Have you ever found yourself standing outside on a really clear, dark night, you know, just looking up at the sky and feeling completely overwhelmed by the sheer scale of it all?
Oh, absolutely. It's a very humbling feeling.
Right. You look at all those stars, all that seemingly empty space, and you just can't help but wonder how much we really don't know about the fundamental mechanics of what's going on up there.
Yeah, we like to think we have it all figured out, but
But we really don't. And, well, today we are going to completely flip the script on one of the most famous, most terrifying objects in the cosmos. We're doing a deep dive into a radical new wave of astrophysics.
radical is definitely the right word for this one.
For sure. Our mission for this deep dive, we want to unpack a revolutionary theory that claims black holes are not just those bottomless cosmic trash cans we've always been told they are,
Right, they might actually be something far more active.
and far more mysterious.
Hmm.
The stakes here are absolutely massive for the scientific community, because this single theory could potentially unify three of the biggest mysteries in the universe.
It's huge.
It really is. It could rewrite our entire understanding of how 68% of the cosmos is powered.
Mm-hmm.
But to help navigate the heavy physics, we need a high-level perspective on where this paradigm shift is actually coming from.
Well, we're looking at some truly groundbreaking research emerging from teams at Arizona State University and the University of Michigan.
So,
And what these researchers are doing is fundamentally challenging the core physics of black holes as we currently understand them.
because, I mean, for decades, the standard scientific consensus has painted black holes as these ultimate dead ends of the universe, right?
Exactly, just these gravitational traps where matter simply falls in, crosses the event horizon, and is, well, lost forever.
Just gone.
Yeah, just gone.
Yeah.
But these teams, they are observing the exact same cosmos and drawing a highly disruptive conclusion. They're proposing a mathematical model that completely alters the macroscopic architecture of the universe.
Okay, let's unpack this. Because the core claim here from Kevin Croker, he's an astrophysicist at ASU, leading a lot of this theoretical work.
Yeah.
It's a total paradigm shift.
It really turns everything on its head.
He's arguing that black holes are not simply matter sinks or cosmic vacuums indiscriminately sucking up everything.
Yeah.
Instead, they are actual functioning engines of dark energy.
Which is a wild concept to wrap your head around.
It is, because calling something an engine implies it's generating an output. How exactly does a collapsed, dead star act as an engine for the entire universe?
To understand that, we have to look at a mechanism called cosmological coupling.
Cosmological coupling.
Right. Normally, under standard general relativity, when we think of matter being absorbed by a black hole, we just assume it gets crushed down into the void.
Squeezed into nothingness.
Exactly. But according to the theory of cosmological coupling, that ingested matter doesn't just vanish into a bottomless pit. It actually undergoes a radical phase transition.
Like it changes state completely.
Yes, it's converted into a specific form of vacuum energy. And what's crucial to grasp here is that this vacuum energy exerts actual physical pressure on the fabric of space-time itself.
So it's not just sitting there passively.
No, it is actively pushing outward.
Okay, so if I'm visualizing this correctly, that pressure isn't just some localized phenomenon happening right near the edge of the black hole.
Not at all.
This transformed energy is actively contributing to the expansion of the universe. It's the invisible force constantly accelerating the separation of galaxies.
That is the absolute core of the argument. It shifts our entire perspective on where dark energy actually originates from.
Which we've been looking for since, what, the late 90s?
Yeah, since the late 1990s, we've known the universe is expanding at an accelerating rate. And cosmologists have just used this placeholder term dark energy for the force driving it.
But its source has always been a ghost.
Right. Anaya Shorty, an astrophysicist at the University of Waterloo, he has this brilliant way of framing it. He compares this cosmic mystery to a classic detective story.
Oh, I love a good detective analogy.
It works perfectly here. Shorty points out that most structures in the universe, normal galaxies, star clusters, nebulae, they have very little, if any, effect on dark energy.
They're just innocent bystanders.
Exactly. But black holes, he calls them the obvious suspect acting suspiciously in the face of an obvious crime.
That is a great quote.
Because their extreme gravity warps space-time more severely than anything else, they are mathematically the most logical candidate for the source of this phenomenon.
Here's where it gets really interesting. To fully grasp how this dark energy engine works, we have to try to look inside the black hole itself.
Which is usually a big no-no in classical physics.
Right, and the central idea of this theory, questions something that's been a staple of theoretical physics for decades, the existence of the singularity.
Yeah, the singularity is traditionally defined as this point of infinite density at the very center of a black hole.
It's the terrifying concept where all the laws of physics completely break down and collapse.
It is. It's the point where our mathematical models essentially fail, producing infinite values that just don't make sense in the physical world.
But Gregory Tarley, an astrophysicist at the University of Michigan, he asserts something entirely different here.
He maintains that the fundamental laws of physics actually survive. Something prevents that ultimate infinite collapse from occurring.
So instead of matter crushing down into an impossibly dense point that defies quantum mechanics,
And matter is halted, and it's transformed directly into pure dark energy.
but wait, this raises an obvious question. If all that stellar material transforms into dark energy pushing outward, why does the black hole still have such massive crushing gravity?
That is a highly intuitive question.
Because if the mass is converted into expansive vacuum energy, shouldn't the gravitational pull just disappear?
You would think so, but it comes down to a fundamental principle of Einstein's general relativity. The external gravitational attraction of an object doesn't actually depend on the specific state of the matter inside it.
It doesn't.
No, gravity is dictated by energy density. Remember, mass and energy are equivalent.
E equals mc squared.
Exactly. So whether the interior is made of crushed rock, collapsed neutron star material, or highly pressurized vacuum energy, as long as the total energy density remains incredibly high, that massive gravitational pull remains completely intact.
So the outside universe still feels the exact same gravitational, well,
Even if the interior has converted into an engine of expansion.
wow. You know, when I was reading through Kevin Croker's research, he used a balloon analogy that really made this click
I
for
think a
me.
balloon analogy is great.
Yeah, imagine a large balloon that represents our universe, right?
Yeah.
And it's filled with millions of tiny, smaller balloons.
Which are the black holes.
Right. As those smaller balloons inside start to inflate, they inevitably push against each other, and the main outer container forcing the entire outer balloon to increase in size.
It's a really useful macroscopic way to visualize the aggregate effect.
It makes it so much more relatable.
It does. But to be scientifically precise, what we're really talking about at the quantum and cosmic scale is a continuous process. Inside these coupled black holes, what's occurring is essentially an inverted Big Bang or Big Crunch happening constantly.
And a constant inverted Big Bang. That sounds intense.
It's a highly dynamic event where matter is eternally converting into the very energy that expands the space-time metric it lives in.
But a single black hole doing this wouldn't noticeably affect the universe on a grand scale, right?
No, not at all. But the total population of billions and billions of these objects generates a massive cumulative thrust. Every single black hole is contributing to this push.
So it's connecting the microscopic physics of a collapsed star directly to the macroscopic structure of the whole cosmos.
Precisely.
We need to pivot to the massive implications of all of this. Because these research teams aren't just trying to explain the anatomy of black holes.
No, the scope is much wider.
This single physical theory is attempting a monumental triple threat. It's proposing a unified solution to three major unknowns in astrophysics: the Hubble tension, the nature of dark matter, and the mass of neutrinos.
Trying to solve even one of these would be a career-defining achievement.
But all three at once, that requires some incredibly elegant physics.
If we connect this to the bigger picture, let's start with the Hubble tension.
Okay, lay it out for us.
For years, cosmologists have faced a deeply frustrating discrepancy when they measure the speed at which the universe is expanding.
Depending on where they look.
Exactly. When they measure the expansion rate in the early universe using the cosmic microwave background, they get one number.
And then,
When they measure the late universe using the light from local supernovas, they get a significantly faster number. It's like having two different speedometers in your car giving you conflicting speeds for the exact same drive.
and traditionally, trying to fix that math has required theorists to invent entirely new exotic particles, or modify the laws of gravity, which just creates a ripple effect of new problems.
It's always a messy workaround, but by introducing this concept of cosmological coupling, the calculations naturally resolve themselves. Because black holes grow and accumulate over cosmic time, the amount of dark energy they pump into the universe also evolves. It isn't a static force.
So it changes as the universe ages.
Right. This means the expansion rate of the universe should change between the early epochs and the modern era. The calculations suddenly show a consistency that bridges that gap perfectly.
And the best part is it relies entirely on standard general relativity. No exotic new physics required.
None at all.
Okay, so that solves the expansion rate. And it also touches on the dark matter problem, since these black holes grow with the universe. But what about the third massive mystery here, neutrinos?
Ah, the ghost particles.
Right. They're famously known as ghost particles because they're incredibly tiny, abundant, and interact with almost nothing.
Trillions of them are passing through your body right now.
Which is always weird to think about. But recent astrophysics data created a massive headache regarding their mass, right?
A mathematical nightmare, frankly. The problem arose with recent observational data from the Dark Energy Spectroscopic Instrument, or DASI, which maps the cosmic web of galaxies.
Okay.
When cosmologists plugged the DSI data into the standard model of cosmology, which rigidly assumes dark energy is a constant, unchanging force, the equations just broke down.
They didn't balance.
No. To make the math balance with the observed clustering of galaxies, the equations force the sum of the neutrino masses to drop below zero. A negative mass.
Which is physically impossible. You
Yeah.
cannot have a particle with less than zero mass. It
Well,
completely breaks our fundamental understanding of reality.
it really does. But this is where the elegance of the coupled black hole model truly shines.
Because it fixes the math.
Exactly. The negative mass was only forced into the equation because scientists were rigidly assuming dark energy was a cosmological constant.
But if it's dynamic,
Yes, when you swap out that constant for a dynamic dark energy, one that evolves because it's being generated by black holes, the entire equation shifts.
so the model mathematically corrects the discrepancy.
It balances the energy budget of the universe, allowing neutrinos to exist with positive mass without breaking the observational data from DASI.
Kevin Croker has this incredibly memorable metaphor about this unified solution. He says, for now, our chair has 3 legs, and we think we can already sit on it.
It's a great way to put it.
It's such a profound statement about the state of this research. What stands out to you about how elegantly this one theory solves 3 massive cosmic headaches?
Well, to build a chair you can actually sit on, you need more than just elegant equations. You need hard, real-world data to back it up.
Right. Theory is just theory without data.
Exactly. And this theory is deeply grounded in fascinating new observational evidence.
The DSI data.
Yes, the Dark Energy Spectroscopic Instrument out in Arizona. The latest measurements from this instrument over the past year suggest something absolutely wild.
What do they find?
They suggest that dark energy might actually be losing intensity over time.
And that directly contradicts the core assumption of the standard model. Because the standard model treats dark energy as an immutable, unchanging property of empty space. If dark energy is just a constant feature of the vacuum, it shouldn't fade.
It should remain exactly the same.
But if black holes are the actual origin of this dark energy force, then that fading intensity makes perfect logical sense.
It aligns perfectly with the cosmic history of star formation.
Okay, break that down for us.
The universe had a period known as cosmic noon, roughly 10 billion years ago, where the formation of massive new stars was at its absolute peak.
Just a massive boom in star creation.
Right. And naturally, as those massive stars burned through their fuel and collapsed, it led to a massive surge in the creation of new black holes.
More stars, more black holes.
But over the billions of years since then, the rate of new star formation has steadily declined.
So fewer new stars being born eventually translates to fewer large stars dying, which means a slower rate of new black holes forming across the universe.
You've got it.
If black holes are the engines pumping dark energy into the space-time metric, a drop in new black hole production means less new dark energy being injected into the system over time.
The fading intensity observed by DSI tracks perfectly with the decline in stellar formation. It fits together like puzzle pieces.
It provides a remarkably cohesive timeline. And because the pieces fit so well, bridging both quantum mechanics and observational astronomy, the momentum behind this idea is just growing exponentially.
It really is. What started in very small theoretical working groups has now expanded into a massive collaboration involving 50 researchers across multiple institutions.
That's a huge shift in the scientific community.
They are taking this incredibly seriously. Right now, scientists are waiting on the next generation of highly detailed galaxy maps from DSI and other surveys to provide the necessary observational data.
They need those maps to definitively confirm if the expansion rate variations match the precise distribution of black holes.
Exactly. The data will be the ultimate judge.
So what does this all mean?
It means we are likely witnessing a fundamental historic shift in our cosmic narrative.
A total rewrite of the textbooks.
Yes. Black holes are transforming in front of our eyes, from terrifying cosmic destroyers, the dead ends of space-time, into the very engines that drive the continuous expansion of our universe.
Resolving historical physics discrepancies along the way.
They're the active agents of dark energy, and the key to solving problems that have plagued scientists for decades.
For you listening to this deep dive, I think this is such a powerful reminder of why staying curious about science is so thrilling.
It shows that the scientific method is never truly settled.
Right. Just when we think we understand the grand mechanics of the universe, and we print the textbooks, assuming dark energy is a static constant and black holes are bottomless pits, a completely new perspective comes along and rewrites the entire story.
It proves that relying on the joy of discovery and critical thinking is so much more valuable than just accepting old dogmas.
I want to leave you with a final, provocative thought to mull over on your own today. We've established that the total population of these black holes acts like smaller balloons, continuously pushing outward on the fabric of space-time.
Yes.
But we also know from observatories like LEGO that black holes frequently orbit each other, collide, and merge in incredibly violent events.
The biggest collisions in the universe.
So if every individual black hole is actively generating vacuum pressure, what happens to the fabric of space-time in that exact moment when two of these massive dark energy engines violently combine into one?
That is a fascinating question.
Does that merger create a sudden, localized burst of cosmic expansion? A sudden ripple of intensely focused dark energy pushing the local universe apart? It is definitely something to think about the next time you look up at the night sky.
Thank you so much for joining us on this deep dive. Keep looking up, keep asking questions, and never stop wondering about the mechanics of the universe.
We will catch you on the next deep dive.